we doing it? I think we're doing it. Hey, okay, so I think we're going. Let me just go. How's the settings? How do I do this? My poor computer, it's struggling with the it's struggling to do all this stuff. Okay, we are live. It says we're live, and it says, oh good, I am streaming in super high quality whatever. Okay, nice. Just wanted to make sure, because on my preview it only says like 380 or 360, sorry. So that does seem to be working. Okay, we're doing it. We're moving. We're doing it. Welcome to MATH1081, the final exam revision. This is weird because I'm also watching myself with a 5-second or 30-second delay. So okay, I can deal with that. Hello, and welcome. I have tea. I have an exam in front of me. I figured out how to do the hotkey switch thingy, so I'm stoked. We can switch between the exam, and occasionally I'll need to write stuff, so we can do that too. Let us chill, breathe. Remember that when you do your exam, it's a performance. Make sure you get yourself a nice beverage before you do your exam, and have a nice, pleasant sleep in the night before your exam, because you can't be expected to perform on the day without sleep. These are the most important things. Make sure that you've finished your studying routine. Your studying schedule needs to finish before the day of the exam, because the rest of the time you're just gonna. I need you to spend that time just preparing yourself physically, because that's how I like to do it. Anyway, let's move on. The comments on the exam. The exam information is going to be pretty much exactly copy and pasted from the Term 2 exam, so let's just read of it together. There are 60 marks in the exam, and the total number of points for each question is going to be apparent to you. For example, this is worth 0 points. Make sure you see that you might have to scroll down to see some parts of the exam, and you need to see that end of exam thing at the bottom. Otherwise, there could be more stuff just hiding below where you're currently looking. What else? It's designed to be 2 hours, but because of internet craziness, we have a 3-hour window to do the question. You'll have a 3-hour window to do the question in. If anything terrible happens, you will need to notify Jonathan Kress. You could notify me, and we'll get you to resit the exam. Hopefully nothing terrible happens. That's fingers crossed. Nothing terrible happens. But if something does happen, should something happen, the first step is to email myself and Jonathan to let us know, and we will sort out what can be done. If you believe there is a mathematical or logical problem, you can describe it at the bottom of this page. If you that down here, there'll be a little thing down there. Where are we? And if there's a bug and there is a bug in Mobius which causes the less than symbol immediately followed by a letter when it's written in a text essay box. Basically, it thinks that's a HTML tag. So don't do that. Don't do a less than symbol followed by a letter, because that will just make Mobius cry. Okay, your answers will be saved every time you hit the next or back button. Use the Mobius syntax checker. I highly advise that one. I was doing a practice exam and I got caught out by that one. Use the syntax checker because you don't want to be losing marks because of syntax. Doesn't guarantee that everything is correct, but it shows you when things are not correct. Text boxes, you can just write your answers in text. And in all the mathematical expressions, every time you need to do mathematics with Maple syntax, you'll be given the syntax you need for that question. So you should never be scratching your head thinking, geez, I wonder what the syntax is for Maple to do permutations or combinations. No. That'll be given to you. Every text box will have that. So the syntax you need will always be there for you. This is not a question on Maple syntax. That's all going to be given. You can bring anything you want with you to the exam. You can bring your pet cat. You can bring your notes that you have prepared. You can use any general source on the internet that is not specifically prepared for this exam. For example, you cannot use a chat service or ask your mates for help. You can't phone a friend. No, you're supposed to do this exam. You're not supposed to use Wolfram Alpha, but you can use a handheld calculator or software like Maple or Python. The idea is with Wolfram Alpha, it's pretty much the same thing as Maple or Python, but Wolfram Alpha does a bit more for you. It's got a bit more smarts to it. And we don't want you using that, but you can use other computational tools like Maple or Python. Because in that way, it's guaranteed to be your own work and not yours plus some. You can use pens or pencils, a ruler and paper and so on. That is permitted. You are allowed to do that. Permitted. How can I access last term's revision? I don't think there was a last term's revision. I'm sorry. And I did one of these this time last year, but I wasn't teaching it last term, and I don't think there is don't think there is a revision stream for anything between now and same time last year. No help is allowed during the exam. I hope that is clear. Don't ask a friend. Don't ask some anonymous person on the internet either. Don't ask your enemies. It's supposed to be your work. And yeah, I think that's fairly self-explanatory. If it's your work, fine. If it's not your work, not fine. Wolfram Alpha is leaning more towards not your work because it's a bit smarter than your average programming language. Yeah, treat it like you would treat it an exam. And if you cannot take if you cannot sit the exam for reasons that are not within your control, maybe some accident befalls you, or just for any reason if there's any reason why you feel you shouldn't take the exam, seek special consideration and do it before the exam. Don't get to the point where you sit the exam and say, geez, I wish I didn't sit that exam. I'm not really feeling up to it. No. You apply before sitting the exam. If you sit the exam and then decide that you're not up to it, that's going to be difficult. That's going to make life difficult for the people who decide whether or not to give you special consideration. So don't do that. If you're just apply beforehand. If there's any issues, nope, we're all good here. All right, let's go. You don't need to write that in the exam, but you can if you want to. All right, let's do it. There's some comments. What do you mean if I can't get a computer to solve the entire question for me? You are the computer. And is there a hurdle requirement for the final exam in order to pass the course? No. You do not need to pass the exam in order to pass the course. Most of you will be sitting on a pretty sweet pre-exam mark anyway, and you don't need to get amazing marks in the exam to be able to pass the course. So if you walk away from the exam saying, gee, I only got a handful of marks, or then you'll still pass the course. Even with a handful of marks, you'll still pass the course. All right, let's do the thing. All right. First question. You're given some sets of pairs from R2, where things, 7x minus that thing, that set, it's a region in the plane. Here's another region in the plane. Here's another region in the plane. 3 regions in the plane. Prove that if you've got a point in the A region and another point in the B region, then your point must be in the C region. Okay. And they've been very nice to you in this one. They've given you some nice... this question has been carefully and lovingly constructed with you in mind to allow you to easily solve this question. Why am I delayed? I'm concerned that you're not seeing what I'm seeing. Have we changed pages? Yes, we should have changed pages, but why does OBS not think we've changed pages? I don't think I'm sharing the right screen. This is the right screen. I've only got one other screen. It's that one. Oh, okay. What if I say to... This is exactly the same problem as I had. Oh no. This session is recorded. There. Alright. It's alright. There's only like 12 pages. I can do this. Oh, damn. There's no escape. Okay. If you're given 3 sets. They're regions in the plane. An A region, a B region, and a C region. Prove that if you're in the A region and if you're in the B region, then you must be in the C region. Be sure to give your carefully written, detailed, and logically correct answer. Full marks will not be given for sketchy work. And don't type this. No, this. That's not okay, because that'll start being rendered as a HTML tag. So just stay away from stuff like that. Okay. We show... Okay. Words. No one wants to see your equation. Start with words. You show that any point that's in the intersection of A and B is also in C. Suppose if xy is a point in A and B, then, well, what do we know about that point? We know 7x minus 6y is greater than or equal to minus 3. And let's call this equation 1. We also know that 4x plus 7y is greater than or equal to minus 5. And let's call this equation 2. Add 1 and 2. And what do you get? 11x plus y is greater than or equal to minus 8. Hence x, y is c. Boom. All you need to do. You don't need to do fancy formatting. You don't need to go, oh, I think I'll center that, or I'll write that in LaTeX syntax. No. Text is fine. Just write it in text. You can see what I'm typing. You can't see what I'm typing, can you? Oh, damn it. So much for a smooth stream. Why? Properties. Not OBS, that one. Okay. Yeah, no one can see what I'm typing, so I just typed it out now. Sorry, there you go. Not Earth. Not my day. Not my turn. Oh, I wonder if I try the exam in Chrome, would that be any better? You know what? I'm going to try that. I'm going to save. Quit and save, just because that might fix things. Grab that. You can see it now, yeah, but I'm just going to switch over to a different browser to see if that fixes the problem. Okay, resume. All right, here we go. And I'll switch that to Google Chrome. Okay, resume. No, that's not doing anything any better. Encoding overloaded. Consider turning down video setting. Ah. Okay. I am just going to pause the stream for a second and hopefully this can fix things. So just hold up. No, we're not. I've got a slightly different idea that I'm going to try. Okay, are we back yet? Okay. La 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 la. We are back. Yay. Okay, we back. Okay. Right. All right. Can that? And you can actually see me when I do stuff now. So if I scroll down, moving, scrolling, doing it. Okay. 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 Let's resume. Let's do this. Technical issues. Okay, so what I was saying before, and you couldn't see what I was saying, so I'll just say it again. You don't need to do fancy stuff like center your equations or type it out in LaTeX. You can just hang on. Now I'm nervous that we're not actually doing. Okay. Is that play? It is playing. Okay. Sorry, I'm terrified that I'm just here by myself. Okay. Okay. I can do this. So, you don't need to do fancy things like center all your equations. I mean, I'm not going to stop you, but just don't bother. You don't need to do LaTeX syntax or anything crazy like that. All right. Let's get on to answering the questions. We've just discovered that the regions, if something's in A and B, then it's also in C. Find a point C, which is in C but not A. Okay. What do I want to do here? Well, how about let's set x to be equal to 0 in those things, and I'll just take y to be -8. because if so 0 minus 8. Just pick one of the points in your set C and check if it's in A or not. Guessing and checking should be enough. Now I'm being clever here by setting x to equal to 0, and I notice the signs of the coefficients here and here are different. So I'm going to get a positive y value in one of them and a negative y value in the other one, so I'm pretty happy that this is going to work. 0 minus 8 is going to be in C, but 0 minus 8, well, that's going to be a positive number on the left-hand side. Actually, no, that's no good. Positive number will be, okay, let's try something different then. Yeah, 0 minus 8 is not going to work. Damn, I was what about 0, 1? Yeah, 0, 1, is that in A? Let's check out 0, 1. That's going to be... -1 is greater than -3. Oh, -6. No, it's going to be -6 greater than -3, which is false, but 1 is greater than -8. So I'm happy with that. 0, 1. 0, 1 sounds good. Yeah, so 0, 1 sounds good to me, because -6 will be not bigger than -3, but 1 will be bigger than -8. Good. So I'm making my life a little bit easier for myself by choosing x to be equal to 0, and you can, yeah, guessing and checking will get you that one. So what have we discovered? We've discovered that the intersection of A and B is in C, because this is anything that's in A and B will be in C, so we know that's true. But we also know there's some stuff in C which is not in A. So we know that A is not C. And let's just check this other stuff. A is B. A intersect B is a proper subset. We know that too. That's also true. It's a proper subset of C, because there's some stuff in C that does not belong to A and therefore cannot be in the intersection. All right, let's press the comforting "How did I do" button to make sure that we're all good here. Yep, looking good. Next question. I think something's gone wrong. YouTube is not receiving enough video to mean a smooth streaming. Users will receive okay, you'll see some buffering. Sorry about that. Which one of these statements is true? The only tricky thing about this question is that A is a set of sets. So you've got, I think we're back. Are we back? I'm not sure. It seems to be working. Okay. OBS is telling me, YouTube is telling me strange things, and now I'm panicking. Okay. The only tricky thing about this is that you've got a set of sets from the numbers 1 up to m squared, and so your sets are not individual numbers. The things that live in A are not individual numbers, but themselves are sets. For example, you've got 484. From here, calculator. And square root 484. 484 is 22 squared. So this is going to be an element of the numbers up to 22 squared is going to be an element of this thing. not itself a subset. Is this going to be an element of some set? Is that an element of some set for yes, it is. It's going to be an element of some set that lives in A. No, hang on. Not that one. That one. That's an element of some set where the set belongs to one of these. And that's not a subset of A, but that will be a subset of A. Oh, yeah. Cool. So just be aware that the things that live in here, all the integers up to a particular square number, are they're the beasts that live inside A. Yeah, A is a set of sets. So just be, yeah, that's all this question is. Okay. You and your friend are considering a congruence where that thing M is given to you, a factorization is given to you, and a factorization of B is given to you. And you don't know what A is, but A is given to you, a range of numbers is given to you. You can assume that 19, 67, and 3,209 are prime. Okay, well, one of those wasn't obvious, but okay. And you may use the table of prime factorizations given at the end of the question. Good idea. Your friend asks you to find all A in that range, for which the congruence has a unique solution modulo M. Provide your answer in the box below. Make sure you read the syntax advice. Syntax advice, give your answer in that form. Okay. Now, when does this thing have a unique solution? It has a unique solution when the number A has a reciprocal in mod M, or in other words, when A and M share no common factors. A and M share no common factors. Now, M has a whole bunch of common factors here, and one of them is 6. Ew. 6, disgusting. So many common factors, so many factors in 6. So we're going to have to get rid of all the even ones, all the multiples of 3, but also all the multiples of 9 and 67. So why don't we shift over? Does this work? Let me just try this. And can you see if I write on here? Can you see that? You can't see that. Okay, never mind. That's annoying. Why can't you see that? Ugh, that's alright. I'll just go back. I'd even figured out how to do hotkeys. Oh, no, wait. Hang on. No, go there. And now you should be able to see. If I go here... Sorry, I'm going... Now you should be able to see it. Yes, you can see it. Aha, ha, ha, ha. I'm learning. I can do this. There. Boom. Here's a whole bunch of prime factorizations for our enjoyment. Now, we want to cross off all the ones that have got a factor of 2, 3, 19, and what was the other one? Basically anything that has a common factor with M. So 2, 3, 19, or 67. So let's go back to our list. Uh, 67, no. 2, no. So, yeah. No, and that's because of the 67. Here there's a 2 and a 3, so that's definitely no. No. That one's okay. I'll buy that. In fact, I can get rid of all the 2s, every second one, because I don't even have to think about those. Get rid of all the second ones, because they have factors of 2, and get rid of all the third ones. Well, that one's already dead, but I'll cross it off again, just to be sure. Double cross, double cross, and that one gets a double cross as well, just for consistency. Then I need to cross off the ones that have a 19 in them. That's that one. Any more 19s? I think that's it. And the 67. So this one, that's got a 67 in it. And I think that's it. Okay, so what have we got left? We've got that one, that one, that one, that one, that one. Oh, and that one. So 1, 2, 3, 4, 5, 6. 6 solutions. Just going to move that window over here so I can read off what I'm doing. Okay, come back here. 2, 2, 4, 4, 7. 2, 2, 4, 5, 1. 2, 2, 4, 5, 3. 2, 2, 4, 5, 7. 2, 2, 4, 5, 9. 2, 2, 4, 6, 5. Any more? No, that's good. And to model good behavior, so, there's a comment. You missed 607. Thank you. 4, 5, 9. To model good behavior, I'm going to look at it. 1, 2, 3, and I missed one of them. Okay. 2, 2, 4, 5, 9. Let's check it out. 1, 2, 3, 4, 5, 6. Hang on. Didn't I write? How many did I write here? 1, 2, 3, 4, 5. Oh, I've written for 2. No, I've written that twice. No, I got that one. I got that one. You're tricking. 6 solutions. Now notice I'm checking the syntax of my answer because it's really easy for that stuff to creep in. So just hit that little button there just to make sure that it looks good. You won't have a how did I do button. I am missing something. Oh no, I did 2. Sorry. Hang on. 2, 2, I'm missing one. 2, 2, 4, 7. 4, 4, 7. 2, 2, 4, 5. That one. 3. No, I got that one. I have to get 2, 2, 4, 5, 3. That one. There we go. Still not quite right. That one. 2, 2, 4, 5, 7. 2, 2, 4, 5, 9. Got that. 2, 2, 4, 6, 3. I didn't have 2, 2, 4, 6, 3. That one. Yay, okay. 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 Slightly different question. Your friend is challenging you to find all the A's in this range for which the congruence has more than one solution modulo M. Okay, so we've just crossed off a whole bunch of them. Now, if this thing, so we'll have to go back again. Now, when does this thing have more than one solution? Well, that's going to be when the M and the B and the A all share a common factor. That's when you get multiple solutions. And in fact, you'll get exactly that many solutions. But the only common factor that this thing shares is well, it's going to have to be a multiple of 67. So if you want multiple solutions to this, you better choose your A value to have a 67 in it. And there's only one value here that has a 67 in it, and that's the first one. So A has to be 224545. Yep. So we notice in this set. Cool. How'd I do? Yay, got it right that time. Okay, next question. Just gonna go and just check chat. What's going on, chat? You got through that too? Yeah. So far, so far. I'll be glad when this stream is over. I don't mind the maths, but my poor little computer's just not handling this at all. Time to get a bigger computer. Okay. My classmate Luna wants to know more about the equivalence relations and equivalence classes in this here polynomial. Let that polynomial define a relation on the set where x and y are equal if their output values are equal. Now remember, this is a cubic, so it's got that kind of S shape to it. Prove it's an equivalence relation. Let's go. So this is pretty bread and butter stuff. So reflexive. If x tilde y, then f of x equals f of y. This means f of y equals f of x, and so y tilde x. Good. You don't need to write a beautiful essay on this. Just show me that you know it's reflexive. Symmetric. No, sorry, that's symmetric, damn it. That's symmetric. X, since f of x is always equal to f of x, x tilde x. See, I know what's going on. It's reflexive, it's symmetric, transitive. If x, y, and y tilde z, then f of x equals f of y, and f of y equals f of z. So f of x equals f of z, and x tilde z. Boom. Cool. That'll do. You don't need to do any more than that. Are we still live? YouTube. Yep, we're still good. We're still good. Okay. Luna also wishes to find the equivalence class of 0 with respect to tilde. Help Luna by answering them box below to make sure you read the syntax advice. So what's the equivalence class of 0? What things are equivalent to 0? In other words, what functions have the same image as f of 0? Now they're the things that are going to map to 25. I'd probably want to switch over to this screen for that one. This is question 5. Yeah. 8125. I'm just going to So f of 0 on one hand, that's just equal to 25, and that's supposed to be equal to f of x, which is equal to x cubed minus 81x plus 25. That's what we got, right? Yeah, minus 81 plus 25. So I can cancel off the 25s. So I get 0 is equal to x cubed minus 81x, which I can also write as x times x squared minus 9 squared. So x can be equal to 0, 9, or minus 9. Okay, we were kind of expecting 0 to be in the equivalence class containing 0, but we also got plus or minus 9. So let's throw those in. 0, minus 9, and positive 9. Your tutor, Dylan. Dylan, he's a good tutor. He challenges you to find a value of x such that the equivalence class of x contains only one element. Give your answer to Dylan as a single number, for example, 1081. You know what? Once this thing's big enough, then it probably... Once it's big enough, that's going to work. Would I bet that 1081 is big enough? You know, if you weren't certain, that's probably going to be good enough. You just need to make it big enough so that you're fine. You probably don't like that answer very much. Let's think about it. Maybe 1081 works, maybe it doesn't. Let's think about it. When is f of x? Or maybe solve. Solve 1081 equals f of x. So 1081 equals to x cubed minus 81x plus 25. So this thing I can take the 25 over and I get 1056 is equal to x cubed minus 81x. It's annoying. See, I know it looks like this. And there's 0, and it's got roots here and here. And I could find the maximum, which is there, and just compare it to that. So that, and you know what, that would be the proper thing to do. So I'm guessing that 1081 is correct. It's probably big enough, but I mean, if I was out of time, I could do that. Because 1081 is going to be way out here somewhere. Way out there. So the proper way to do it, it's to find the local maximum. F prime of x is equal to 3x squared minus 81. X is equal to, what's that going to be? Plus or minus 3 root 3. So here's minus 3 root 3. And then you throw that back into the equation, you figure out what x is. But you know what? 1081 is going to be so enormously far beyond whatever that is. I'm just going to put in 1081. Because that's going to work, damn it. Not that one. That one. So I'm going to put in 1081. I mean, you could solve it properly, or you could just put in 1081. Your tutor also wants to know, wants you to answer true or false and give them brief reason for the following statement. There exists X such that the equivalence class of X contains exactly 2 elements. That's going to be true, and of course that's going to happen precisely when X is equal to plus or minus 3 root 3. Okay, that's probably too brief. This happens when X is plus or minus 3 root 3. Shall we say a horizontal A. Just a little bit more. What I said before was probably too brief. So that's just give them a reason to let them to award you all the marks. Finally, your tutor Dylan wants you to help Luna by answering the following true or false and give them a brief reason for the statement. There exists an X with more than 1,000 elements. That's craziness. And we'll say each. The equivalence classes have at most 3 elements, and I don't really want to say anything more than that. All right, next question. This tutor, yeah, but he's your friend. You know Dylan. He's a good guy. Okay. A tetragroup. Okay. Is an object studied in the field of mathematical topodynamics. All right. A tetragroup may be doubly Euclidean or not, and it may be sporadic or not. You are given a list of statements concerning a tetragroup X. Some of these statements are logically equivalent. They're just different ways of saying the same thing. Group the statements into logically equivalent sets and enter your answer below as a list of sets separated by commas. Okay, so that syntax. Okay, I need to think about these. That's a bit strange for me. Let's get a new page going. And we'll paste that in. That one. What is this all about? So I want to write this down in terms of language that I can recognize, which is in terms of logical statements. We will let E mean or represent. You can't see my writing. And let's say S. X is sporadic. Sporadic. Yeah, sporadic. Then, well, we can do something with these things here. X is doubly Euclidean, or it's not sporadic. So that means X is either Euclidean or not sporadic, which I might write in the equivalent way S implies E, because that's going to be easier for my brain later on. 2. X is double Euclidean only if X is sporadic. Alright, so that's Euclidean implies sporadic. 3. If X is not sporadic, so not sporadic, then it's double Euclidean. 4. If X is double Euclidean, then it is sporadic. So I know that's the same as this one. Boom. 2 and 4 are the same. 5. X is doubly Euclidean and X is not sporadic. So that's E and not S. 6. X is sporadic if doubly Euclidean. So that one goes Euclidean implies sporadic. 7. Double Euclidean or sporadic. 8. If sporadic, then Euclidean. That one. So I've seen a few of these before. That's the same as that. S implies E. Do I have that anywhere? Oh, E. These two are the same. That's the same. That's equivalent as not S implies E. So that's the same as 3. S implies E seems to be... Oh, that's the same as number 1. Boom. Gotcha. 1 and 8. This has got an and in it, so I'm kind of expecting that to be by itself. Cool. And I think I've got everything else covered. Alright, let's chuck that in. So I think 1 and 8 are the same. 2, 4, and 6 are the same. And 5 is by itself. And 3 and 7 are the same. How are we doing? Yay! Huh. Not that one, I want that one. How many questions will there be in the final exam? It depends. This question involves, so there's 60 marks. You are not told how many questions that's divided into, but you do know there are 60 marks, and it will be made apparent to you where those marks lie in the different questions. For example, this question here, I know this is worth 5 points. Okay. This question involves determining whether it is possible to deduce the truth or falsity. Deduce the veracity of a given statement, given the 3 propositional formulae, these things. Given those things are true, is it possible to deduce with certainty whether P is true or false? Select one option, give reasons. Now, there's all sorts of different tools in your toolbox when you're faced with questions like this. My personal favorite, table. There's 3 variables plus those 3 parts. So I'm going to say 6 rows. Might go 7 rows because I want a final one. And 8 possible variable combinations. Plus 1 for the headings makes 9. Headers are in the first row. Alignment center. Cool. The truth. The truth table. Let's go. Okay. So P. Q and R. and I'll call this part 1, part 2, part 3. Oh, and I guess I didn't need all. I've done this the wrong way around. 1, 2, 3, 4, 5, 6. Yeah, that's not right. Other way around. Delete. Cancel. Delete table. I want 9 rows and 7 columns. Headers in the first row. The truth table is still a good caption. Okay. P, Q, R. Statement 1. Statement 2. Statement 3. And then over here I'll have 1 and 2 and 3. Okay. And I'll use false, 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 true, 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 false, false, true, true, false, false, true, true, false, true, false, true, false, true, false, true. Boom! Let's do the thing. P or Q. That's going to be false, true, true, true. It's going to be true everywhere. No, false there. And then true, 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 true. Q implies junk. Well, the first place I'm going to do is go look through all the places where Q is false and say that's vacuously true. So it's there, 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 and there. And then in the places where Q is true, I have to look and make sure that P or R is true. And that's going to be false there, true there, true there, and true there. And similarly with 3, I'll look through in all the places where R is false and makes it vacuously true. So I don't even have to think about those ones, vacuously true. These ones, P and Q have to be true. So it's going to be false, that's going to be false, that's going to be false, and that's going to be true. And then when is 1, 2, and 3 all true? Not there, not there, not there, not there, yes there, not there, yes there, and yes there. Okay, good. I've pulled out the truth table. Now, in those rows, in the rows where all these 3 statements are true, we can then look back and see what's happening to P. And we see that in these rows here, not that. Can I bold font that? Yeah. Could I do like color? Background color, yes. Whee! No, that's not. Here. Green. No. Green. I just want green text. There. Good. I just want green T's. There. There. And there. They're the only ones. And in all these other ones, I don't even need to worry about them. Because they're bad Fs. False. Good. Okay. So I have a thing with tables, okay? I like my tables to be nice. In the rows where the propositions 1, 2, and 3 are true, what can we say about P? P is always true. Boom. Why is that true? Because that P is true in the rows where 1, 2, and 3 are. Boom. This is what I'm talking about. That one, and that one. Okay. Righty. You could have done that maybe a faster way, but I like my tables. Do we get extra marks for using pretty colors? Hot pink? If Sadly, no. You only get extra style points in your mind, which is just as good as having hot marks in Math1081. Okay. Given that the same three statements is true, is it possible to deduce with certainty whether Q is true or false? Could you please help Manav by selecting one option? Well, in those statements, Q is sometimes true and sometimes false, so it's impossible to say with certainty, because if P equals true, Q equals false, and R equals true, maybe so slightly differently, because the propositions 1, 2, and 3 are true if that, but also when P equals true, Q equals true, and R equals true or false. But who cares? Who cares what R is equal to? R is equal to whatever. But let's just say true for consistency, because propositions 1, 2, 3 are all true if P is that combination. So Q can. P can be true or false. Or you could just copy and paste the whole truth table in again, but this is nice. Alright. Is that all good? Boom. Cool. Okay. Let x be a real number. Prove that if x is an integer if and only if that stuff is true. Be sure to set out your argument clearly and logically. Carelessly. Do not recklessly write your proofs. You might need to think about this one for a second. But let me just show you an example. Yeah, I'd encourage you to think about this one. It's not obvious how you might want to proceed here. You may start writing a proof and then decide halfway through that you don't like that proof and try it again. My advice to you is to use your pen and paper to do this stuff, because the pen and paper will help organize things in your brain. I'm going to do it this way. If suppose x is an integer, then, well, what can we say about the floor? Floor of 608x is somewhere, well, the floor, it's going to be less than, it's always going to round something down, so it's going to be less than or equal to 0.0608x. Could be equal to it, but it's going to round it down. So it's going to be 0.0608x minus 1. But importantly, that will never be equals on the left-hand side, because you'll never round down by a whole integer. So you've got that. And you've also got the same thing with the ceiling. Ceil of 0.392x. What's this one going to do? Now the ceiling always rounds up. So you're going to go, whatever the ceiling does, it's going to be 0.392x. It's always going to be bigger or equal to than 0.392x. Whatever x is, it's going to be bigger than that. But it's also going to be bound on the other side by 0.392x minus 1. Now that's not bigger than or equal to, because you'll never go a whole integer up. Ceiling will round it, so you'll never get an equality there. It's always going to be that. And then I'm just going to add these two things together. The sum of these two equations gives, well, the left-hand sides that plus that is less than, strictly less than, floor plus seal. Which is strictly less than that. Which is equal to x minus, that should be a plus 1. And that's going to be x minus 1. Good. So whatever this thing is, it's strictly between, I might save that for the next line. Whatever this stuff is, it's going to be less than x plus 1. It's somewhere between x minus 1, strictly between x minus 1 and x plus 1. The only integer in this range is x. So maybe, but it's not clear that floor plus seal must be an integer, so maybe I'll say since the good. So we needed to do something to say that it's definitely in that. That's definitely true. Okay, now we need to do it the other way around. How do I do this the other way around? For some reason, when I was doing this at home, I thought that's easy. Do I want to say suppose x is not an integer? Maybe I want to say suppose x is not an integer and do a counterexample. Yeah, let's do that. No, it is easy. Let x equal pi. The sum of the left-hand side will be rational, the right-hand side not rational. Suppose x equals pi is not an integer. Then the left hand is an integer. So then I'm proving the contrapositive. That if x is not an integer, then the sum of those two things can't be equal. So maybe I'll make it a little bit more clear what I'm proving. We show the converse of if So not the converse, the contrapositive. No, can you just convert? We show the contrapositive of that. We prove the contrapositive. If x is not an, then is not equal to that. Yeah, so we're it's easier to prove the so one of these was easy because you just needed to show that if you just pick a non-integer value of x and show that this doesn't work. And what's your favorite non-integer value of x? Maybe it's pi, maybe it's root 2. The left-hand side's always going to be an integer. The right-hand side ain't. Okay. Isn't the codomain of floor and seal integers, so the sum is... Yeah, that's exactly right. Okay. I think I'm reading your comment too late. But anyway, that's nice. That's nice. Let's move on. Hudson. He's always hounding me about these things. He's interested in counting the number of solutions to an equation under various conditions, such as this one. Hudson wishes to count the number of solutions to this equation where those things are non-negative integers and various other conditions may hold too. Okay, and tells you how to do the syntax. You can use P or C. And help Hudson out. Okay, when there's no other conditions. Well, this one's just classic stars and bars. So that's just 10 plus, I'll do is 23 plus 10 minus 1, 10 minus 1. Boom. How's that, Hudson? You like that? There you go. The number of solutions where every k is congruent to 5 modulo 0, where everything is a multiple of 5, you got no chance, mate. If everything's a multiple of 5, then the left-hand side's a multiple of 5, but the right-hand side ain't. Easy peasy. No solutions. You crazy. There's no solutions where everything is congruent to 0 modulo 5. Why? Every xk is 0 mod 5, then that's, yeah, maximum 50 words. You know what, I can do it in 20. I can do it in half as much. No troubles. The number of solutions in which every xk is congruent to 0 to 5 or 2. That's interesting. 5 or 2. So some of them can be 5 and some of them can be multiples of 5, some of them can be multiples of 2. What's the equation again? Okay. So some of them can be congruent to 5 mod 0, some of them can be congruent to 2 mod 0. So there's a few ways this can go down. You could have one of them congruent to 5 mod 0, and then the remaining, that's going to make, yeah, and the remaining 9 variables congruent to 2 mods. Let me read it again. There's 10 variables. You could have one of them congruent to 0 mod 5. So it's equal to 5k. Or could equal to 2 mod 5. Okay. So it's 5k plus 2. So let's break this down. I need to think about this. New page. You'll just go new. Discard that stuff. So So we've got x1 plus x10 equals 23, was it? Yeah, 23. And you can be congruent to 0 of 2 mod 5. And x k can be congruent to 0 mod 5, or xk can be congruent to 2 mod 5. Okay, so let's think about how many let's think about how many 2's we can have. You can't have just one 2 because you've got to make the rest add up to 21. You can't have 2 because then it'll have to add up to 19. You can't have 3 because the remaining will be mod 5 and it'll have to add up to 17. But you can have 4. You can have 4 xk's congruent to 2 mod 5 and the rest will add up to 15. Okay, so if 4 xk's xk to 2 mod, then let yk be equal to 2 plus, then xk. Those xk's are equal to 5yk plus 2 for some y. Okay, they're non-negative integers, so boom. And xk just equal to 5yk for some other yk's. So you can have 4 of them congruent to 2. That will then x1 plus da 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 plus x10 is equal to, well, you've got 5 of them. They're all equal to y1, 5y1 plus 5y10 plus an extra 8, which is equal to 23. And then if you take the 8 from both sides, you'll get 5y1 plus 5y10 is equal to 15. You just divide by 5, y1 plus y10 equals 3. Awesome. And we can solve that. We just know there are from 3 plus 10 minus 1, choose 10 minus 1 solution. Alright, so that's if there are 4 congruent to 2 mod 5. What if there's more? What if there's more? Well, you can't have 5 of them, because then you won't be able to get the rest to add up again. You can't have 6, 7, 8, but you can have 9. So maybe I'll just say similarly. If 9 xk's then, well, what are you going to get? You'll get x1 plus x10 is going to be equal to 5y1 plus 5y10, which is plus all those 2's, and there's going to be 9 times 2 of them, so it's 18, is equal to 23, and you'll get most of these cancelling off. Y1 plus y10, take the common factor of 5 out of there, is equal to 5, so everything's equal to, so all that stuff's equal to 1. and that just tells you there are, from 1, you just need to choose which one to put it in. 1 plus 10, choose 1. Whew! Okay. Okay, so there's 2 cases. One where you've got 4 2s and everything else, and 4 2s and 6 5 congruent, 4 congruent to 2 and 6 congruent to 0, or 9 congruent to 2 and 1 congruent to 0. So we just need to figure out how to do this. How to break it into those cases. So the number of solutions where it's congruent to 0 mod 5 or 2 mod 5. Well, how are we doing this? There's the first case was where we had 4 of them congruent to 2. So we need to choose from our 9 variables 4 of them to be congruent to 2. And I don't really care which ones they are. There's 9 choose 4 ways of doing that. And I can do that in 3 plus 10 minus 1 choose 10 minus 1 ways. And the other case was I had 9 2s and 1 5. Well, I can do that in from my 10 variables I had to choose 4. From my 10 variables I have to choose 9 to make to promote into congruent mod blah blah blah, words. I have to choose 9 of them to be congruent to 2 mod 5, and then once I've done that, there are from 1 plus 10 minus 1, choose 10 minus 1 ways. And I'm going to hit this thing just so I can make sure I got all my brackets. And it renders that, what? I guess that is, okay. I guess that's true. Thank you for simplifying that for me. Give a detailed explanation of the answer. Okay, we break into cases. Case 1, if there are 4 to 2 mod 5. And 6. Then x1 plus x10 equals 5y1 plus 5y10 plus 2 times 4 equals, what was it, 23? Equals, what was it? Take that over, divide by 3, that. Choose the variables in from 10 variables, choose 4 ways. Then see from 3 plus 10 minus 1, choose 10 minus 1 solutions. Centering, just because I'm pedantic. You know what? Boom. Let's make... You don't have to do the bold font thing, capital case, Case 2, if there are 9 variables congruent to, and the rest congruent to, blah, 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 9. So that's equal to 1. Choose 9 ways, 1. Okay. Did I get it right? Let's hope so. Oh yeah. Okay. Cool. Next question. Oh, here we go for time. Okay. The English alphabet contains 26 letters. 21 are consonants and there are 5 vowels. Not all alphabets are the same, so it's nice to clarify. UNSW Intelligence Agency. Oh dear. Okay. UNSW in tag wants you and your friend Jack to assist their efforts. Congratulations, you've been recruited to the UNSW Intelligence Agency. And you're going to help them solve their problems concerning words. These are concerning words made from the letters of the English alphabet. Right. And here's all your syntax help. How many 17-letter words contain the letter W exactly once? Now, they're not really words in the sense of dictionaries. Oh, my dictionary's arrived, by the way. This is... Oh, you can't see me. I'm over here now. Hello. No, I'm over here. Stay. Naughty camera. Dictionary. Anyways, driving my camera crazy. Let's put that there. That's the part A. Letter A, part 1. Okay, are you following me? You are following me. That's nice. Okay. How many 17-letter words contain the letter W exactly 16 times? Well, we'll choose where to put the letter W, and there's 17 possible choices, and I need to choose 6 of those places to be a letter W. And then I can choose the rest of the word any way I like. So there's 25 letters to choose from, and I need to plonk them in another. I need 11 of them. So, words. How many 17-letter words are there which contain W exactly 6 times and M exactly 6 times? Okay. Well, it's basically the same thing. I choose my 6 ways to put the W's in, and then I've got 11 places, and I need to choose 6 of them to put the M's in, and then I can fill out the rest of the word. There's only 24 letters to choose from, and how many have I got? I've used up 12. I've got another 5 to go. No, I don't. 17-letter words. I didn't put a C. Syntax checking. See? Didn't put the C in. Let that be a lesson to us all. How many 17-letter words which contain at least one consonant exactly 6 times? That's a nice question. How many? So and the person who wrote this question is being very nice to you, because they're really holding your hand and helping you see that this is a inclusion-exclusion principle question. And you know what, I might do the careful reasoning for down here. We use the inclusion principle. The number of with how shall I express this? Let A exactly 6 times. Then we want the size of A. Then that thing is equal to, well, that's going to be the size of all the individual sets. A. That looks like an emoji. I'm sure that's an emoji, like happy face thing. B. They all look like emojis now that I've seen it. Minus the size of the intersections. A. Okay, and I don't have to worry about triple intersections because there's 6 letters in each, because I'll never get more than that. And I can simplify this a bit because that's going to be 26 times, you know what, 26 times that one. I'll use AW because that was the one given to me in part B. And this is going to be from 26 choose 2 times the size of the intersection. A W intersect A M. Nice. So it's 26 times my answer to part A. Minus from 26 choose 2 times my answer to part B. Nice question. I wish I wrote that question. No? Did I not? Did I forget a C again? Did I forget a plus? What have I done? Oh, is it only I can only choose consonants. Ugh. Fine. So not A. Thank you. Yeah, they're not. Damn it! I got done by the consonants. Okay, so 21. And there's 21 choose 2. Ugh. Okay, there you go. You got me. You got me, consonants. How many 17-letter words are there which have no repeated letters and include swan as a subword? Okay, so no repeated letters. So S, W, A, and N don't get repeated. That makes the question a bit nicer. So I can the way you do this is you treat the word swan as a special word. So treat that as like an aleph or a special character. We've got 26 original letters, and we've removed 4, so we've got 22 letters to choose from for the rest of the word. Swan can go in any of the 17 original places, and from the rest of it, we've got 22, and we have to choose the remaining. We just used 4, so remaining 13 from 22. Yeah, 22, 13. Is that correct? No. Ugh. I have to think about this again. I should really write this stuff down. Fine. I'll write it down. Okay. So you've got this word swan. Let swan be equal to aleph. Be a special character. Oh, because it's maybe it goes this way. How many say aleph B, C, D, X. So you've got that counts for 4 words, and then this counts for 4 letters, and then this counts for 13. I can add up, making 17. Yeah. Or I could go B, then the aleph, C, D, X, or B, C, D, X, aleph. So there's how many possible choices for the how many possible choices for the aleph do I have? Aleph counts for 4 possible. There's 14 possible positions here. So 14. Our special character. And then for the rest of them, I've just got to choose. Well, I can choose. And then I just have to fill out the rest of the word. First up the letter. There are 26 original letters. I can choose 22 choices. Second. That's going to give me 21 other choices. And all the way down to the 13th letter. That gives me 22 minus 13 is 9 choices. So (14 times 22 times 9 equals 14, 22 factorial over 11 factorial. Okay, so 14, P, 22, 13. Better. T. I'm supposed to eat the tea. Ugh, gross. W1 is a... Oh, I have to give reasons for my answer? No, I don't. Good. We say that a word is a spread subword if the letters of W1 occur in the same order but not necessarily consecutive ways. For example, maths is a spread subword of that. And also of that, how many 17 letter words are there which have no repeated letters and include swan as a spread subword. Okay, so instead of having a single position for... Instead of choosing a single position for my characters S, W, A, and N, I have to choose a whole bunch of different ones. So from my 17 positions, I have to choose 4. And I don't really care the order. I just have to choose 4 positions. And then I'll populate them with S, W, A, N. And then the rest of the letter can get filled out in the same way. So it's very similar. I just get more than 14 possible choices. Whee! Okay. Choose the 4. In 17. Cool. Give non-reckless answers to your for your reasons for your answer. All right, next question. Hopefully I can do this. How many questions are left? Oh God, 15 questions. Ugh. I can do this. I can do it.
Aren't there less than 17 places for swan since it has a length of 4 letters, so there would be 17. Yeah, 17 minus 4 plus 1.
Don't rush because I'm not Russian. Thank you. Okay, what is correct about this recurrence? It's an order 2 recurrence. Order 2 because it goes back 2 steps. It's linear. Yes, it is. Linear recurs to the fact that these are all kind of these are there's no n terms. In fact, it's that. It's not homogeneous. It's not any of the others. How did I do? I did okay. Yeah, none of the coefficients here are variables, so that makes it a linear. It's linear in terms of these ANs. Sure, they can have linear coefficients. That's fine. Well, there's no like AN squareds or anything crazy like that going on. Yeah, so they're just AN minus 1, AN minus 2. They occur without. It's not sine of AN minus 1. That would be a non-linear coefficient, a non-linear recurrence. First, consider the associated homogeneous equation. This recurrence has a solution like that for 2 values of r. What are the 2 values? Well, you end up solving a quadratic, and the quadratic in this case solves to, what is that? 12 and 2, no. 8 and 3. 8 and 3. So that's minus 8 and positive 3. Yay. So find a solution to the initial value problem here. Okay, so if you know it looks like just need to copy some of that down. Okay. So suppose an is equal to something times minus 8 to the n plus some other thing times 3 to the n. Then a0, well a0, what is a0? That's just going to be a plus b. And suppose a plus b is equal to minus 1, and a1 is going to be equal to minus 8a plus 3b, and that's equal to minus 14. Equations 1 and 2. Maybe we'll do equation 2 plus 8 times equation 1. That sounds like fun. We will get 8b plus 3b is 11b, and then minus 4 minus 8 is equal to minus 4 minus 8. I can do minus 12. That doesn't sound right. It's plus 3b. That's 14. Let's try adding those again. I think I need more tea. You know what? I'm just gonna walk out the door for a moment and get myself more tea because I can't add any more. My adding abilities have left. 8, 11, and then minus 14 plus 8 is 22. Yeah. So b is minus 2, which means a minus 2, and a is equal to 1. My abilities to do normal things have left me. I'm going to get more tea, and because I only have to walk like 3 meters, I will be back in a moment. Oh. Okay. Right. I'm back. Even just knowing there's tea there makes me feel better. An is equal to negative 8. The n minus 2 times 3 to the n. Already forgotten what it was. Minus 2 times 3 to the n. Okay. We now return to the recurrence. There's an 8 to the n there, which is different to minus 8 to the n, so I don't need to worry about anything like that. But what I've got here is a degree 1 polynomial times 8 to the n, which means what I have to guess is a degree 1 polynomial times 8 to the n as my solution. How did we go? Yay. Right, and I've got tea. More exam advice for you. It's tea. Have tea. Okay. You have a weighted graph, and the weighted graph has those vertices. You want to find a minimum spanning tree. Ah, good. Minimum spanning tree. The edges of the graph and their weights are listed below. Select all edges which make up your minimal spanning tree. It is recommended that you draw the... This is always a good idea. Recommended you draw the tree. I'm not surprised. Let's put that there. Okay. You don't need to submit your drawing. Good. There are 13 edges in the list. Make sure you don't miss any. Hint, it should be obvious without any calculation how many edges you should select. Yes, because you always have one less edge than the number of vertices. So you've got 1, 2, 3, 4, 5, 6, 7, 8 vertices, which means you need 7 edges. Let's draw this while we go through. Behold the power of Kruskal's algorithm. All you need to do is go through the list, ensuring you get all the cheapest, from cheapest edges to most expensive edges, and never make a loop. So let's go through getting the ones. There's no ones. We'll get the twos. We'll take that and that. GB and CB. I'm just going to draw it while I got it here. G, B, C, CB. I've got those ones. And they were cheap. They only cost 2. The next ones I'm going to get are BA. I'll get that. BD. They're all coming from A. From B. BA, BD. A, D. That's 3. That's a 3. CG. I don't want that. So I'll get the first 2, but not that one. Okay, let's do those. So yes, I want you, but I don't want you. Bad, because that would make a loop. And then I'll go through and check out all the 4s. What 4s do I want? No. HF. And CA. CA. No, I don't want CA. That would make a loop. But I did get HF. Alright, what else do I want? I have to go through the 5s. There's no 5s. 6s. No 6s. 7s. DA. I don't want DA. CH. Oh, yeah, I'll take CH. Perfect. That's my tree. That's me tree. I took CH. Alrighty. And I said I needed this. Let's just count. 1, 2, 3, 4, 5, 6, 7, 8. 8 vertices, which means I need 7 edges. 1, 2, 3, 4, 5, 6. What? I didn't click something. 1, 2, 3, 4, 5, 6, 2. 7, 8. Am I missing an edge? I'm missing an edge. I need one more edge. Let's keep going then. What have I missed? A, B, C, D. I don't have E. Huh. Okay, so let's just keep. We went through the 7s. Now we'll go through the 8s. There's EH. That's expensive. E. There we go. There. Okay, now let's check it again, because that seemed to work for us before. 1, 2, 3, 4, 5, 6, 7, 8 vertices. So we should have 7 edges. 1, 2, 3, 4, 5, 6, 7 edges. How did I do? I did good. Alright. From list above, find the edge of smallest weight that you did not choose. Name this edge in the essay box and briefly explain why you... To Adam. Hi, Adam. I didn't choose... what did I not choose? GC, because it would makes with GB and BC. "15 words. I don't like talking to Adam. I'm not going to say 50 words to him unless I really have to. Does your answer to A give a tree of shortest paths in the original graph from F to all other vertices? And of course not. That would be totally unreasonable. That's what Dijkstra's algorithm does, not Kruskal's. Answer yes or no, and give a brief answer. Well, let's think about it first. From F, what does F look like? F looks like that. Does it give the tree of shortest paths from F to other stuff? Well, I can get from, I'm looking here, I can get from A to F for 8. I can go straight there. That's worth 8. And to get there using this tree, I have to go all the way around. So no, definitely not. That's a no. FHCBA. No. Which has weight. What was my weight? 4 plus 7 plus 2 plus 3, that's 16. But I can get there for half that. Has a smaller weight of 8. Yeah. And that's that question. Yay. Graph G has 4 vertices, A, B, C, D. Taking the vertices in that order, the graph has adjacency matrix that. Okay. Does it have loops? Yes, it's got a loop right here. And 2 loops there. 2 paths of length 1 form. So not to A, not to B, that one, and that one. Does the graph contain any parallel multiple edges between different vertices? If so, give examples. Yep. A to C. A, C. So A, C. That's what these mean. There's 2 paths of length 1 from A to C. Find the number of walks of length 3 from vertex D to vertex D. Okay. Is that what M looks like? Yeah. And because it's an adjacency matrix, what I really want to do is M times M times M. And what does that give me? That. And I want to go from D to D. That's that entry down there, that bottom one. Right there. And so that's 40. 40. Are we good? Are we good, Maple? Yes, we are. Find the explanation. Explanation. Is it 4, 4? Yes. Oh, not that. Copy. Yes. Oh. Okay. That's probably a bit terse. You might want to not answer as tersely as that. But senior lecturer Mansfield answers tersely like that. Because I've got the how did I do button. Oh dear. I'm getting, yeah, I think I'm reaching my limit. How many questions to go? One more. This one and one more. Okay, I can do this. I can do this without getting silly. There are 3 problems below concerning a simple connected graphs G with whose degrees are given. For each graph you have to answer 2 questions. Is it tree? And is it possible for the graph with the given degrees to be planar? How many regions would be in that planar representation? If not planar, then... So it's simple, connected, but possibly not planar. In some of the following, there may be many vertices having the same degree. Make sure you count the vertices carefully. Okay, so the graph has vertices. This is its vertex degree sequence. Is it a tree? Well, it's got 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 vertices. It's connected. And how many edges does that have? So add that. Now the sum of the vertex degrees divided by 2 is the number of edges. We've got 9 vertices, 8 edges. It's a connected graph. It must be a tree. Yes. How many regions does a tree have? 1. Just the whole enclosing region. The graph G2 has vertices with those degrees. Is it a tree? Well, let's add those up. How many edges would that graph have? The handshaking lemma tells us that we can just add all the vertex degrees, and that's then take half, and 21 that's a lot of edges. 21 edges, and you've got 1, 2, 3, 4, 5, 6, 7, 8. You've got 21 edges, and your graph only has 8 vertices. Now you might remember there's a theorem that says when you have the more edges you add into a graph, there comes a point when the graph can no longer be planar, and that point occurs, of course, somewhere between when you start adding edges and when you've got the kind of maximal complete graph. There's this kind of cutoff point, and that cutoff point is when you've got 3 times v minus 6 edges. So we just discovered, and how many vertices do we say you have? 1, 2, 3, 4, 5, 6, 7, 8. We've got 8 vertices. So this is question 14. Satisfies E is going to be less than or equal to 3v minus 6. And we just discovered there were 21 edges. Since 21, that's less than or equal to 3 times 8 minus 6, which is 24 minus 6, which is, I can do 24 minus 6, that's 18. Oh dear, that's not true. That's not true. It's not true that the number of edges is at most 3 times the number of vertices minus 6. Hence it cannot be planar. Not planar. It's certainly not a tree. I mean, geez, you've got so many edges here. No way is it a tree. But it's not even planar. Vertex with this vertex, tree, possibly tree with this vertex degree sequence. Be ye a tree. First, let's figure out how many edges you got. "14 edges. That's not so bad. And you've got 1, 2, 3, 4, 5, 6, 7, 8, 9. Lost count. 1, 2, 3, 4, 5, 6, 7, 8, 9. You've got 9 edges, 9 vertices, and only 13 edges. That's too many to be a tree, so you're definitely not a tree. And how many regions? Well, I reckon this is a planar graph. And if it's a planar graph, you've got E. What did we say E was? E was 14. If then V plus R equals E plus 2. Since this is 14C, since E is 14, V is 9, then R is 14 plus 2 minus 9, 16 minus 9 is 7. 7 regions. Yeah, it doesn't have so many edges that it can't be planar. It's kind of a weird question because it's not clear to me. Could I draw this? Could I draw this in such a way that it contains K33, for example? Maybe I can. In fact, that's interesting. So I've got. Let's try and draw this so that it contains K33. So we'll start off with a 1, 2, 3, 1, 2, 3. So we can have edges coming out there, coming out there, coming out there. So it's not necessarily clear to me that just based on this sequence of vertex degrees that it should be planar. So we've got 3 ones of degree 3. We get 3 other vertices. These can be my 3s. 3, 3, 3. I'll put a 4, 5, and 5 over here. And I need 3 more edges. 3 more. So I have 1. That can be my 1, 2, and 2. 2 and 2, and that's got to be a 1. And I need to add 2 edges here. 1, 2. 2 edges here. 1, 2, 1. Boom. Non-planar representation. So it might be. See, I don't have to draw it this way. Don't have to draw it this way. All I know is the vertex degree sequence. I could draw it in any number of other ways. It's not clear to me that based on this vertex degree sequence that it is planar or not. I'm going to put 7 there anyway because I think that's a good response, but I'm also going to go back to question 1. Issues with the exam. In 14C is so in question in 14C Yeah, we don't know. Take that, exam. That's what I think. Okay. I'm still going to say 7 because if I'm going to roll the dice here and say that I think they intended this to be a 7, find out. Yeah, they did. I'll have words to the person who wrote this exam. In the meantime, that's what they meant to ask. Well, that's the answer they meant you to arrive at, and they didn't quite do a very good job of making sure you got there. Next, end of exam. Thank goodness. I was done. Yay. Okay.
Is this real live? Yes, this is real live. What tea should I get
To maximize focus, T2 Buddha's Tears loose leaf scented green tea. For maximum MATH1081 insight and exam marks. By only Buddha's Tears, use the MATH1081 promo code to get a 10% discount.
Can you check anyways with E less than or equal to 3v minus 6?
That's just an upper bound. It doesn't tell you if it's planar or not. Just because you have less. I mean, we could check the calculation. This graph certainly has less than the required number of. I mean, let's just do the calculation. So E, which is equal to 14, is that less than or equal to 3 times 9 minus 6? Well, 3 times 9 minus 6 is, I can do this, 27, that's 21. Yeah, so you're easily within the bounds. This limit here only tells you what happens when you've got lots and lots of edges. You've got too many edges to even think about being planar. It doesn't work both ways, though. If you want it to work both ways, you need to be using Kuratowski's theorem. This inequality here is just a really nice, hard and fast way of saying, look, you've just got way too many edges to even consider being planar. Just get out of here. You ain't planar. Here we have a graph that's not planar but does satisfy the inequality, and that shows you that the converse is not true. If you've got too many edges, as in more edges than 3v minus 6, then get out of here. You ain't planar. But if you've got less edges than that, well, I might have to look more carefully to decide if you're planar or not, because there's some examples that do satisfy that inequality and yet fail to be planar. That's really Kuratowski's theorem that you should be using there.
This stream brought to you by T2 Buddha Tears. Exactly. You prefer coffee? I don't have any coffee.
But I do have hot water and T2 Buddha's Tears. Buy now, just in time for Christmas. But not in time for your exams, which is on Wednesday, unless you actually go to the shops and get stuff. All right, let's finish here because I'm done. Take care of yourselves, lovely people, and good luck in your exams and the rest of your mathematical careers. It's been my pleasure to be your guide through the wonderful world of discrete mathematics. And I hope to see you around campus next year, because it looks like we'll be opening, fingers crossed, knock on wood. Nothing terrible happens between now and when we're supposed to open up. So, good luck, all the best, and I will catch you next time.
But would you say our exam is harder than this, or similarly in difficulty?
You can't ask me questions like that. That's asking for extra information. Just no response on what the exam looks like. 60 marks, roughly similar to what you see here. Take care, everybody. And of course it looks easy when I do it, because I'm the one here who's suffering, and you're just like, Daniel can do 3 times 9 minus 6. I make it look easy. Sure. I'll see you later, everybody.